Hello friends, my name is Prunjay Kumar Gaurav. Today I will discuss about the formula related to hydraulic turbine. First of all, efficiency of turbine. There are various types of efficiency of turbine. First type of efficiency is hydraulic efficiency. It can be represented by eta H or hydraulic efficiency. It is equal to power given by water to runner upon power supplied by water at the inlet of turbine, or it can be written as it hydraulic efficiency is equal to runner power upon water power. It can be represented by runner power upon water power. Runner power means the power which is given to runner, and water power which is the supplied water supplied by water power supplied by water at the inlet of turbine. Now runner power is equal to rho a v1 vw1 plus minus vw2 into u upon 1000 kilowatt. V into W into Vw1 plus minus Vw2 into U upon G into 1000. W is equal to M into G. For Pelton wheel or Pelton turbine, runner power is equal to W into in the bracket Vw1 U1 plus minus Vw2 U2 for radial turbine. Water power. Water power is equal to mgh upon 1000 kilowatt, or it can be written as W into H upon 1000 kilowatt. W is equal to weight of fluid striking per second. Next, it can be written as rho GQ into H upon 1000 kilowatt for all flowing fluids. For water power is equal to rho QH. Rho is equal to 1000 for water. Rho is equal to 1000. Rho is equal to 1000 kilogram per meter cube for water. Mechanical efficiency eta m is equal to power available at the shaft of turbine to the power given by water to the runner, or it can be written as mechanical efficiency is equal to shaft power upon runner power, which is equal to 2 pi nt upon 60, or it can be written as omega t, where omega is the angular velocity and t is equal to torque. It can be further written as rho a v1 in the bracket vw1 plus minus vw2 into u upon 1000. Volumetric efficiency eta v. Volumetric efficiency eta v is equal to volume of water actually striking the runner upon volume of water supplied to the turbine. Volumetric efficiency. It can be further written as volumetric efficiency is equal to Q actual upon Q theoretical. Next type of efficiency is overall efficiency. Overall efficiency, it can be also called as turbine efficiency. Overall efficiency available at the shaft top. Overall efficiency available at the shaft of turbine upon power supplied by water at inlet of turbine. It is equal to overall efficiency. It can be further also written as overall efficiency is equal to shaft power upon water power. It can be written as shaft power upon water power. Overall efficiency is equal to mechanical efficiency into hydraulic efficiency. Overall efficiency is equal to mechanical efficiency into hydraulic efficiency. If efficiency of generator is given eta g, then efficiency of hydroelectric plant is equal to efficiency of hydroelectric power plant is equal to eta overall efficiency into generator efficiency, and eta p is equal to eta naught into eta g. Classification of hydraulic turbine. According to the type of energy at inlet, the hydraulic turbine can be classified as impulse turbine and reaction or impulse reaction turbine. Impulse turbine is that turbine in which inlet energy is only kinetic energy. For example, Pelton turbine is an example of impulse turbine. Reaction or impulse reaction turbine. In this type of turbine, both kinetic energy and pressure energy at inlet is present. Reaction or impulse turbine is that turbine in which inlet energy is both kinetic and at inlet in kinetic energy and pressure energy both exist. Such kind of turbine are Francis turbine. Francis turbine is an example of reaction or impulse reaction turbine. Third type of turbine are pure reaction turbine. The turbine in which at the inlet only pressure energy available, then it is called as pure reaction turbine. According to direction of flow through runner, the turbine can be further classified as tangential flow turbine and tangential flow turbine, radial flow turbine and axial flow turbine. According to the direction of flow through runner, there are three types of hydraulic turbine. In the tangential flow turbine, direction of flow is tangential. Example, Pelton wheel. In the reaction in the radial flow turbine, direction of flow is radially inward and outward. For example, Francis turbine is an example of radial flow turbine. Third type of turbine is axial flow turbine. In this type of turbine, direction of flow is direction of flow is parallel to the axis of shaft. Direction in this axial flow turbine, the flow direction of flow is parallel to the axis of the shaft. This is the suppose that this is the axis of shaft, then the flow is parallel to this axis. This is called as axial flow turbine. Uh, for example, Kaplan and propeller turbine is example of axial flow turbine. Mixed flow turbine. The in a turbine in which flow is radially at inlet and axially at outlet, then this type of turbine is known as mixed flow. The turbine in which flow is radially at inlet and axially at outlet, then this type of turbine is known as mixed flow turbine. For example, modern Francis turbine is an example of mixed flow turbine. Now, a third classification is according to the head available at the inlet. According to the head available at the inlet, the turbine can be classified into three categories, such as high head turbine, medium head turbine, and low head turbine. In the high head turbine, head available at inlet of the turbine is greater than 260 meter. Head available at the inlet of turbine is greater than 260 meter. For example, Pelton turbine is an example of high head turbine. The next type of turbine is medium head turbine, in which the head available at the inlet of turbine is between 260 meter to 60 meter, or it varies between 60 meter to 260 meter, then it is known as medium head turbine. Examples of this turbine is Francis turbine. Francis turbine is an example of medium head turbine, which head varies between 260 meter to 60 meter. Third type of turbine is low head turbine. When the head at the inlet of the turbine is less than 50 meter, then it is known as low head turbine. For example, propeller turbine is an example of low head turbine. In the propeller turbine, the head available at the inlet is less than 50 meter, so that it is called as low head turbine. Kaplan and propeller turbines are examples of this type of turbine. According to the specific speed of the turbine, The next classification of the turbine is according to its specific speed. Then first we discuss about what is specific speed. Specific speed is that speed in which at the turbine acts at unit pressure, unit power and unit head. When the turbine acts at unit power and unit head, then that speed is known as specific speed. Speed is inversely proportional to net head to the power 5 by 4. Then we will discuss further classification according to the specific speed turbine. So then first low specific speed turbine. It specific speed varies between 30 to 60, and specific speed is varies between 30 to 60. For example, Pelton turbine is an example of low specific speed turbine. Medium specific speed turbine is Francis turbine. For this, the specific speed range is 60 to 300. For high specific speed turbine, the range of specific speed is between 300 to 1000. The example of this type of turbine is Kaplan and propeller turbine is high specific speed turbine. Radial flow reaction turbines. This is a radial turbine in which water flows radially or inward or outward. In the reaction turbine, energy at inlet of turbine is kinetic energy and pressure energy. As water flows through runner under pressure is that part of pressure energy converted to kinetic energy. Runner always full of water and casing. Main part of radial flow turbines. Here are given the main parts related to radial flow turbine. Runner, volute casing or spiral casing or scroll casing, draft tube, guide blade on wicket gate, water from penstoke. Here are a schematic diagram is given of radial flow turbine, which are as in this is a casing, outward casing. This is known as volute casing or spiral casing. Here is draft tube given. Here is shaft given. It is runner, and this is the water is coming from penstoke. Casing runner always full of water. Spiral casing may be spiral shape, reducing cross section area. Inward radial flow turbine. Here is given schematic diagram of the inward radial flow turbine. Here is a schematic diagram is given a guide vane shaft, guide vane shaft, mounting vanes, guide vanes, and there is also given the water flows from casing to stationary guide vane to moving vanes or runner. Water flows over inward radial direction. Discharge does not discharge does not increase inner diameter of runner. Negative centrifugal head decreases relative velocity of water at outlet. Negative centrifugal head speed control very effective. Tendency to wheel to race nil. Turbine adjusts the speed by itself.